All right, so what we know how to solve first order differential equations. In particular, we know how to solve separable differential equations. We know how to solve linear ones. We know how to solve exact ones. And then there's sort of this whole clump of them that can be solved using some sort of substitution. And that if we have that substitution, that we'll be able to get it back to one of the forms that we already knew, separable, linear, or exact. And most of the time we're looking for it to reduce to a separable or a linear. We don't typically reduce to an exact. But if you're thinking about methods that will come up again in the future, separable and linear are definitely a little bit more important than the exact. But if we think about what's new, so what's to come in the next week or so, all right, we're going to be learning about solving higher order differential equations. All right, so solve higher order differential equations. For us, the focus will be on second order, meaning we'll have a y double prime, okay? But the methods that we learn here can be extended to be third order, fourth order, fifth order, et cetera, okay? And when we're looking at these higher order differential equations, we're going to split them into two classes. All right. The first class we will be looking at is homogeneous in variety. Okay, so we're going to look at homogeneous differential equations. And for right now, I want us to really root that in the idea that we have some differential equation equals 0. Okay. The other variety will be non-homogeneous. That we will have some differential equation equal to a function. Okay. And so we're going to start with the easier case, which is when the equation equals 0, or the homogeneous cases. And in our homogeneous case, we're going to take a look at sort of two categories once again. Okay. So we're going to look at a situation where we have non-constant coefficients. And then we're going to look at situations where we have constant coefficients. All right. So we're going to be doing a lot of math, a lot of algebra, et cetera, but the bigger picture here is that the non-constant coefficients is what we're focusing on in 4.2, whereas tomorrow, when we focus on 4.3, we'll really be looking at constant coefficients, okay? Then next week, we're going to take a look at non-homogeneous equations. And in particular, we're going to look at the same categories. We're going to look at non-constant coefficients, as well as constant coefficients. Right? And for the non-constant, that's actually going to be coming up in section 4.7. All right, so we'll see it again at the end. We're going to start with non-constant coefficients in the homogeneous variety. We're going to end with non-constant coefficients of the non-homogeneous variety. And with the constant coefficients, we're going to take a look at sections 4.4. and 4.6, all right? So we're not going to be covering all of chapter 4. I think that is a big order, a big ask in a regular semester, but particularly in a accelerated course, what we're trying to do here is make sure we get all of the ones that we know might come up again. And so there's a little bit more leeway in a differential equations course than perhaps like a Calc 1 course, okay? So I have chosen these because they match things that I've seen in later classes. So I wouldn't be too nervous that we're gonna not cover something that you'll definitely need in a later class. Okay, that's still very much on my radar. Now, one thing I do want to note is that 4.1 is sort of a conceptual section, which is fine and good. And we are going to cover it. But with 4.1, we're going to sort of sprinkle the concepts in as needed. Okay, so as we come to things that require us to unpack the concepts and the theory a little bit more that were in 4.1, we'll sort of sprinkle them into 4.2, 4.3, 4.4, 4.6, and 4.7. Okay. And so that, my friends, is sort of a roadmap of where we are headed in the next chapter, okay? I believe that if you look at the summer schedule on Canvas, that the next exam, exam 2, will be on Monday, July 26th, okay? So we still have this week, next week, the week after, but it will only cover 5.1, chapter 4 and a little of chapter 5, okay? So we'll have a little bit of time between exam, the end of content for exam 2 and the actual exam, and we can, so it won't be like 2.5 weeks worth of content, it'll be a little bit less than that, okay? All right, so all of that being said, we are going to start our journey on solving higher order differential equations with taking a look at homogeneous differential equations, particularly those kinds with non-constant coefficients. All right, so here we are. Things that we know, we've already talked about this, so I don't want to dive too deeply into that. But this should be a good summary of our first few chapters in differential equations. And what's new for today, we're going to solve homogeneous second order differential equations with non-constant coefficients. And here's one more visual for you to really root in this idea of what we're doing and help organize that in your brain. But the big takeaway for today, conceptually, what we're going to be saying is if we have a differential equation and we have one solution, then we can find the second solution. All right, so if we have the differential equation and we have one solution, we're going to be able to find the second one. And so let's begin. All right, so we have a differential equation here. How do I know that this is a second order differential equation?
Y double prime?
Exactly, that Y double prime right there is our key indicator that we indeed have a second order differential equation. All right, and what is our indicator this is homogeneous?
It's equal to 0.
Exactly, this in the orange, that 0 is the clue that it is homogeneous. All right. Now, let's say on an exam in 2.5 weeks or even on the homework, how do we know that we're going to be using the methods from section 4.2? Well, we're given, oh gosh, we are given one solution and we want to find the general solution. And in order to find the general solution, we need to find the second solution. Okay. So the things in the yellow tell us about second order, the things in the orange tell us about homogeneous, but the things in pink are what tie it back to section 4.2. All right. And so I haven't looked at your exams yet. I don't know what your experience was like with the exam, but if you felt like it was really hard to decide which one was which, something like this, as you sort of study and look over your notes, might be useful where you're looking for those keywords and those indicators. Okay. All right, so let's take a look at our second order differential equation. And now one of the weirdest things about differential equations is we actually assume a lot of stuff, okay? And we use this framework of I'm gonna assume something and then let me see if it's true. And if it's true, then it means my assumption was right, okay? I know that's weird logic. Let's just go with it though, all right? And so here is our assumption. We are going to assume that the second solution, so y sub 2, equals some function times y sub 1. All right, so we're going to assume that the second solution is a product of the first solution and some other function. Another way of writing this might be v of x to represent our sum function times y sub 1. Okay. So we're going to start with that assumption. And our first sort of general process that we're going to do is we are going to make substitutions into the given differential equation that reduce the second order differential equation to a first order differential equation. Okay, so we're going to make some substitutions. These substitutions are going to be clever so that we can take this second degree or the second order that we don't know how to solve, turn it into a first order that we do know how to solve. All right. So let's take a look at these substitutions. I'm going to take this expression, and instead of saying v of x, I'm just going to call it v because y is also really y of x. Okay. So one of the substitutions I'm going to make is that y2 equals v times y1. Now, I don't know if you remember on like the first day of class, and I was like, we're going to verify that these solutions are true. And we're going to take our function, plug it in here. We're going to take our first derivative, plug it in here. We're going to take our second derivative, plug it in here. And if it's all true, then we're good to go. And we're going to take a similar approach now where we have y2, and I want us to find y2 prime, and then also find y2 double prime. Okay, this is going to be the start to our substitution. So when we take our y2 and we want to find the derivative, we 100% better use product rule. In fact, we will get v prime y1 plus v times y1 prime. Okay, so like in symbols, that would be what I do generically. But we actually have a function for y1. So let's go ahead and use that, the pink function. So instead of y2 equals v y1, we're going to say that it's vx to the negative 1. All right. So this comes from the pink part above, that we have that first solution. Now, if we use that to write a more specific y2 prime, we will get v prime x to the negative 1 plus v times negative 1x to the negative 2. Or we can clean that up to be v prime x to the negative 1 minus vx to the negative 2. All right, so we found our first derivative. We got to find our second derivative. Guess how many times we have to use product rule? Better use product rule here. Better use product rule here. Okay, so this first group and this second one will each have 2 terms. So I'm going to take the derivative of the first clump, v double prime x to the negative 1, and then plus v prime, v prime, and times negative 1 x to the negative 2. All right, we'll take the product rule of the second clump. I'm going to put parentheses around this because I see that minus sign in front. And if I don't do brackets, I'm likely to distribute incorrectly. Okay. All right, so my derivative here will be v prime x to the negative 2 plus v negative 2x to the negative 3. Right. Let's rewrite this. Let's see if we have any like terms, and let's group them. So we have v double prime x to the negative 1 minus v prime x to the negative 2 minus v prime x to the negative 2. And then minus and minus should be plus 2vx to the negative 3. If we group our like terms, we'll find that we have 2vx to the negative 3, that was the last one, minus 2v prime x to the negative 2 plus v double prime x to the negative 1. All right, so we've taken some derivatives, we've substituted in our first solution. But when I say make substitutions, I mean, we're gonna make a whole lot of substitutions. Right now, what we're gonna do is everywhere we see, let me start here. Everywhere we see a y, we're gonna put vx to the negative 1. Everywhere we see y prime, we're going to put our first derivative. And everywhere we see a y double prime, we'll put this. Okay, so lots of substitutions. Be really careful about this step. So here's sort of our first substitution, our second one. And so what we end up getting is, let's see, the equation starts off with 2x squared, that's gonna stay. And then I'm gonna grab this y double prime to put in here. And that substitutes the first term. Now I need to do plus xy prime, so plus x, and then my new way of saying y prime. So v prime x to the negative 1 minus v x to the negative 2. And we're going to finish off with minus 3y equals 0. So minus 3 vx to the negative 1 equals 0. So let me just pause for a moment. I know that's a lot of writing. How are we doing in terms of the process that we've made our first substitution, our second substitution? All right. So what are we going to do with this massive equation? Well, we are going to distribute, and we are going to combine like terms. And we are going to be so very careful because we've got primes and negative ones and so many different symbols. We just have to be really accurate in this step, okay? So what do we get? We get 4v x to the negative 1 minus 4v prime plus 2x v prime, double prime. Okay, all of that comes from the first clump. Then the second one, we have just a v prime minus vx to the negative 1. And then in the third clump, minus 3vx to the negative 1 equals 0. If you're worried, how am I going to keep track of whether everything is right or not? In this next step, you will know if you're right, but you will also know if you're wrong, okay? Here's how you're going to know. You're going to go through, you're going to see what things you can group together. Let's see what we can group together. I have 4 vx to the negative 1. And then I subtract 1, and then I subtract another 3 of them. How many do I have left? Exactly. We're going to have 0 of those left. And so what do we have on this left-hand side? We actually have 2xv double prime minus 4v prime equals 0. Okay. So how do you know if you've done this substitution correctly? No more terms with v in them. Okay. So when you get to this very last line, it's okay to have a v prime. It's okay to have a v double prime. You should not have any more v's. All right.
So are we missing a v prime term down there, Judy? Sorry.
Are we? Oh, we are.
4v prime plus 2x v prime plus v prime.
Yeah, this negative 4 plus 1 should give us a negative 3, yeah?
Correct.
Yeah, cool. Oh my gosh. Okay. Cool. You should clearly always double check your signs too, even if you have your notes right next to you, because that's another place you could make a mistake. But the bigger place that mistakes often happen is in that pre-distribution phase. When you're distributing, you might not distribute correctly, and you might still end up with a V somewhere, or maybe you mixed up a sign. So at the end, one really good indicator is if you have no more V's, you're probably good to go. obviously, case in point, it's worth a double check, right? So we've gotten to this differential equation. But our original goal was to make substitutions so that we have not a second order, but a first order differential equation. So here's what we're going to do. And I think this is super nerdy, but super cool. We are going to let W, okay, we're going to introduce another letter here. We're going to let W equal V prime. What does that make W prime? Bingo. Exactly. If we have W equals V prime, then when we take the derivative of the left-hand side, well, we sure better take the derivative of the right-hand side. Now let's make that substitution. 2x W prime minus 3W equals 0. Let me get this all back on one page for us. We made some substitutions. We assumed that we had the second solution that happened to be the product of some function and the first solution. We did what we learned on the very first day about finding derivatives and plugging them into the differential equation. And after a whole lot of algebra, we ended up with a much more simple second order differential equation. It's more simple, but it's still a second order. So we had to make a third and final substitution. And we were able to end up with a first order differential equation. Okay. Let's go ahead and finish this problem. So we made our substitutions into the given differential equation that reduced the first or the second order differential equation to a first order. And now we are going to solve the first order differential equation. Okay, so we're going to solve the first order differential equation. And then as a third step, we will write our final answer. All right, so I'm going to grab this differential equation. Let's write it here. 2x w prime minus 3w equals 0. All right. What kind of differential equation is this? All right, let's see. If we were to separate it, maybe a good thing would be 2x dw dx equals 3w. Okay. Let me move all my x's to the right-hand side, all my w's to the right-hand side. Since I have constants on both sides, let's move them both to the side with the x, all right? So I'm gonna have dw over w equals 3 over 2x dx. And we're gonna integrate. All right, so the integral of 1 over w dw equals, let's go ahead and pull that constant out, 3/2 the integral of 1 over x dx. All right, we're gonna natural log on both sides, natural log of w, and then 3/2 natural log of x plus c. We need to have that constant on the right-hand side. I'm going to exponentiate both sides. So I will get w equals x to the, oops, c x to the 3 halves. All right, so I definitely skipped a few steps here. We took this coefficient, we brought it up as a power, and then we exponentiated both sides. And we know from all the work from the previous chapters that that coefficient now is a c in the front. Okay. You can solve this using separable, using separation of variables, and I would 100% recommend that. How else could you have solved this? And we won't go through it, but I think sometimes we only use one way to solve it. And so if we're looking for extra practice problems on a particular method, it's nice to be able to use more than one method so you can double check your answer. Yeah. Yeah, go ahead.
I was gonna say same thing. It's all good.
Yeah, this is a linear differential equation. You could also find your multiplying factor. So if you wanted to practice that, if maybe you felt like that didn't go as well on exam 1, this is a nice chance to say, I'm going to try a different method to do that, okay? And while there are so many resources out there on the internet for differential equations, I think one thing that is important to just be very much on your radar is just because some program or some person chose to solve it in a certain way doesn't mean that that is the best way to do it. It's depending on your strengths and maybe the context of the situation, okay? So we've got this function w equals c x to the 3 halves, but in order to complete this problem, we need to, and let's maybe, we need to go ahead and get everything back in terms of x's and y's. All right, that's where we were starting with our question, and so therefore that is where we must finish with our question. All right, so let's find our final answer. And for us in this context, it often means we're going to unpack all of the substitution. So we know that w equals c x to the 3 halves. We also know that w equals v prime. So we're going to say that v prime equals c x to the 3 halves. If I have v prime, I can find v by integrating. And if I clean this up, let's see, this will be 2/5 x to the 5 halves plus some other constant that'll hang out here for just a little bit. Right. But one thing that I want us to notice here is that c and 2/5 are both constants, right? C and 2/5 are both constant. So as weird as this is, we can actually write this. Okay, so it's not that the 2/5 went away, it's that we're absorbing it into the other constant. Similarly, we are absorbing the impact of that little k in with this constant. So we're almost there. We have v equals something, but we don't want v, we want y2, okay? So let's go back up for a moment, because this right here, our very first line, that helps us find our y2. So y2 equals v times x to the negative 1. That's what we're going to use to find our y2. So y2 equals v times y1, which is x to the 5/2 times x to the negative 1. X to the 5/2 minus 2/2 is 3/2. Okay. Now, something that we're going to learn and talk a little bit more about tomorrow is there's something called the principle of superposition. It's a very fancy sounding word, principle of superposition. And we'll talk more about what that is tomorrow and why that is, all right? But the basic gist of this is that my general solution will be of the following form. We're gonna have our first solution, so C1Y1, plus whatever constant C2 that goes with the second solution. And if we write these as, gosh, you should have been relatively fresh out of linear algebra. If we write these as a linear combination, all right, so C1Y1 plus C2Y2 is a linear combination, it will actually give us all of the solutions. And so we're going to fill in our y1 and our y2, and we'll get y equals c1 x to the negative 1 plus c2 x to the 3/2. So we did all that substitution. We solved our first order using skills that we learned in the last 2.5 weeks. And then we unpacked it all so that we could get a solution that involved the letters that we started with. Okay, let me get that all on one screen for us. This is a big beefy problem. You'll notice there's only 2 questions for today because I didn't know how long they were going to take. But I think we have plenty of time for questions. What are our thoughts here?
I kind of missed, can you please tell us how you got y2 from v, like in the very last steps?
Like this one?
Yeah, please.
Absolutely. So where did I get that from? I got that from my assumption. I assumed that if I know one solution, that to find the other one, I'm going to multiply by some function. And I just called that function v of x. Why did I choose to assume that? We're just going to go with that for right now. All right, it is very much in the flavor of differential equations. We're going to assume this thing, and then we're going to use it as long as everything works out. All right, but that assumption is what led us to being able to substitute back in at the end. Any other questions?
I have a quick question.
Yeah, go ahead.
How is K absorbed in C when you're doing the integral of the last step, the final answer?
Yeah, so when we're looking at these, we have so many constants that sort of pop up along the way that I think the phrase is we play fast and loose with constants in differential equations. And so we tend to just try and boil them down to one constant for each term that sort of catches all of the other constants that came up along the way. Like we've accounted for them all. We're just saying we accounted for them as a single coefficient to make our computations easier.
I sort of understand the gist of that, but I feel like you're a constant plus a constant. I don't know. It is fast and loose. You're right.
It is. And I think maybe we can think about this like whatever number these two become, it's not like C times 2/5 plus K gives you the new one. It doesn't work like that. But it's like C times 2/5 will give us some constant. And then we had something else that we added to the entire function, and the overall impact of that can be written as a single coefficient in the front.
Okay, I think I get it.
It's okay to not get it. It's actually good to be so skeptical, because it sounds like, I think the folks who were very well trained, like I have to write a C for everything, this is very new and different. But it basically comes down to the fact that the more C's and K's we have, the harder it is to find those values. And so the more we can clump them together as one, then we're able to actually find those values. That's sort of the short answer. But let's go maybe see if there's any more questions on here, and then we'll take a look at the second example. And if we have time, we'll actually probably start 4.3 today. All right. Well, questions later are absolutely fine. I think a lot of this actually requires some time to marinate. But let's take a look at example number 2. Okay. So example 2 says, note that y sub 1 equals x is a solution to this differential equation, and find the general solution for the homogeneous second order differential equation. Right, so the structure of the question is very similar to the first one. The parts in the pink tell me I have to go through that same process as before. The y double prime tells me I have a second order differential equation, and my equals 0 tells me I have a homogeneous second order differential equation. Okay. Now, let's go back up to the top for a moment, because I said that, or did I write this? That today we were going to focus on non-constant coefficients. All right, so what did I mean by that? Because I think that's an important clue to also tie into this section. Well, what I mean by that is if we look in this previous question, look at our coefficients. 2x squared, that's not a constant. X, that's not a constant. -3, that one is a constant, but all three of these can be considered non-constant coefficients, all right? And in particular, it's this one and this one that make us use the process that we're using. But the questions we're gonna see in 4.3, all the things in the green circles, those are all going to be numbers. So it's going to look very similar, except we will have numbers, not functions. Okay. And so let's double check that example 2 indeed has non-constant coefficient. Here's one, here's the other. This one would have been considered is a constant, but these two are not. And so we group these under our non-constant coefficient category. All right. So let's make some assumptions. We're going to assume the following. We're going to assume that y2 equals v y1, or rather the product of a function and the first solution. So in our case, y2 is just Vx, right? That is our assumption that we are now going to build everything off of. We're going to start by making a bunch of substitutions. These substitutions, there will be 3 of them, should get us to a first order differential equation. All right, I got y2 equals Vx. Let's find y2 prime. Let's find y2 double prime. Right? We're going to be using product rules, so we need to make sure we keep that in the forefront. All right. So we should be, for y2 prime, be getting some version of v times 1 plus v prime times x. And then we're going to use product rule, but only for the second term, right? The first term we can leave as v prime plus, what do we have? V prime times 1 plus v double prime times x. Right, so this became this, and the second term became the second 2 terms. And we can cluster the v primes into 2v prime plus v double prime x. All right, we're going to take these 3 lovely expressions. We're going to put them into our differential equation. In other words, all the things that are circled in green are going to stay, but our y double prime, our y prime, and our y get substituted with what we have here. And so we have x squared 2v prime plus v double prime x. And then we have plus 2x y prime, so v plus v prime x. And then minus 2y or minus 2vx. All right, so let's just make sure we've done that substitution correctly. Looks like everything is good. And now we distribute, and we know that we should no longer have any v terms. Anything that's just a v should be completely gone after we reduce. All right, so 2x squared v prime plus v double prime x cubed plus 2vx plus 2v prime x squared minus 2vx equals 0. Excellent. My 2vx and my negative 2vx cancel out. Every other term has a v prime or a v double prime, but no v. So I could do a little happy dance and say, yay. Now, I don't want to do a preemptive celebratory. I want to make sure I combine my terms right. We don't want to make the mistake I made in the first one, but I think we should end up with v double prime x cubed plus 4x squared v prime is going to equal 0. Okay. Now we're going to make a substitution so that we turn our second order into a first order. This will give us x cubed w prime plus 4x squared w equals 0. Okay. So I think this equation was a little bit less gross than the other one. And I think we're seeing the process for a second time. We feeling okay about the substitution process? We have any questions on where things came from or where things went? All right. All right, let's get on with our solving then. We're going to solve our first order differential equation. All right. So what do we have? We have x cubed dw dx plus 4x squared w equals 0. What type of differential equation do we have here? We have a linear, yeah. Could we separate? What are our thoughts? Can we separate this differential equation?
So put 4x squared y on one side and then divide everything by x cubed, so you isolate dw.
Exactly, exactly. This one is 100% separable. You can, like the other one, work on it using linear. Is there a procedure that we would like to see? Would we prefer to see linear? Would we prefer to see separable? Okay, we could definitely do linear. I think that it is definitely a separable. If I were solving this on my own, I would go with separable like you all did earlier, but I do think that sometimes like the other ones become, you know, the other processes also need a little love. So if we were to think about that, we would want to make sure that we divide through by that x cubed first, right? So we get w prime plus 4 over x, w equals 0. And what we can do that way is now find our multiplying factor. And what does that get us? Well, e to the 4 natural log of x, e to the natural log of x to the 4th, which will give us x to the 4th. Now, it's okay for me to drop those absolute values because I'm going to be raising something to the 4th power, which means that this x to the 4th will always be positive. Okay. So we found our multiplying factor. We want to go back to our w prime expression, multiply it through. We get x to the 4th, w prime, plus, let's be careful here, 4 over x times x to the 4th gives me 4x cubed, w equals 0. And this might be the nicest version of linear we've seen. I think this is very clear that we have the derivative of x to the 4th times w. Right? No sneaky chain rules. I know that x to the 4th has a derivative of 4x cubed, and I know w has a derivative of y prime. And now I'm going to integrate both sides, and the integral of 0 is just c. And then I get W equals Cx to the negative 4. All right. Since I know I'm going to be writing a final answer where I unpack everything and put it back in terms of the variables I was given, and this isn't too hard to isolate and make explicit, I just went ahead and made it explicit. Okay. All right, so now we have our W, but what we don't have is a V or a Y. And the most important part is we get back to the Y. All right, so we unpack this a little bit. Instead of V, we have W prime equals Cx to the negative 4. We integrate. Turns out this is just the power rule. So negative 1/3 x to the negative 3 plus k. All right, so we're seeing this structure again. The C and the negative 1/3, those we can clump together as a constant. I think that makes sense in our brain. We also compensate for this plus k by grouping them all together and just saying I have a new coefficient of k, or C, and then x to the negative 3. Okay, so we found our V, but how do we find our Y? Well, Y2 was V times Y1. So V, we'll just grab the function part because we're going to roll all those constants in at the end anyway, times x, which gives us x to the negative 2. And then our general solution, we want to be y equals a linear combination of these pieces, C1y1 plus C2y2. And we're just going to plug in our y1 and our y2. And the reason I didn't bring this C in with my y2 is because I knew I was going to give it a constant anyway. So it's still just going to be that constant. All right, so we get y equals C1x plus C2x to the negative 2. And there we have our general solution. Okay. So how we feeling here? Questions, comments, concerns?
And so tomorrow, are we going to figure out how to solve for C1 and C2? Or how does this play?
Okay, that's a great question. So we will take a look at some examples. And so how you would find C1 and C2 is if we had given initial conditions here, okay? And so let me sort of write those off to the side. We might have initial conditions. Now, this is a question I asked us like a few weeks ago, but I said, if we have a second order, how many initial conditions might we need? If we have a third order, how many might we need? Turns out it correlates to the degree. And so you're going to get one initial condition that'll be like y of something equals something. Okay. You'll get a second initial condition that's like y prime of something equals something else. And you're going to be able to use these initial conditions to find your C1 and your C2.
Okay, that makes sense. Thank you.
Yeah, so the thing with differential equations is higher order doesn't necessarily mean different techniques. A lot of it is getting back to techniques that we know and sometimes using those techniques more than one time. Okay. So if there are no other questions right now, I'm going to stop this recording